Welcome to Module 6. So in this module, we will be studying a basic but a very powerful modeling technique. And this technique is where we will be branching into the area of machine learning. And I'm sure you've all heard of machine learning. So this technique can be used to do predictions, just like regression. We can do predictions on quantitative and qualitative response variables. In fact, it is very popular in the case of binary qualitative variables where you have two outcomes, yes or no, or 0 or 1. And as you know, we just studied logistic regression last week that is used to do predictions on binary variables. And so this is another technique that can be used. Um, and what you're seeing right now is an example of a decision tree. And so decision tree is essentially just kind of like a flow chart, uh, like tree structure. So where each internal node denotes a test on an attribute, and each branch represents an outcome of the test. Okay, so as you can see, the nodes here, they represent a test on an attribute. For example, here the question is, what is the loan amount? So that's kind of like a test. Does the applicant have experience? Another test. And then each branch, as I said, is an outcome of the test. So this branch, for example, says the loan amount is less than or equal to 69,500. This is greater than 69,500. So these are kind of like the outcome of the test that is performed on the node. And then each um, leaf node, it's also called like a terminal node, holds a class variable. Okay, so in this case, you have either um, the decision is safe or risky, or here it's risky. These are terminal nodes. And the terminal nodes will always, in the case of, for example, a qualitative binary variable will contain um, kind of like a decision or a class label. Okay, so that is essentially the type of model we will be working with. And the first natural question is, what is the criteria that is used to do this test here at the node? So how do we know that we need to split this data here um, by the loan amount less than or equal to 69,500 or 69,500 greater than? So how do we know this should be the splitting criteria? That is the idea behind decision trees. They are able to do these splits that are most optimal using some metrics that we will be studying, and then this is how the model is built. Okay, so you will see in some cases the tree can be very long, and in our case, at least for this module, we will not be working with too complicated of trees, but I think you get the idea. Now, before we go to the assignment prep, um, one natural question here is, what are some advantages of a decision tree? So why should we use a decision tree to model? Well, first, as you can see, they're very simple to understand, simple to explain to someone, and easily visualized, right? And if there's a way that we can come up with, where we can do these splits optimally, then this is actually a pretty good modeling technique because not only you can explain it to someone, you can visualize this, you can, um, it's much easier to understand than some of the concepts that we have already studied in this course. So that's a pretty big advantage of decision tree. It's also requires uh, not too much data to prepare, and We also do not need a lot of the work that goes into some of the other models. For example, if you remember, we had to create dummy variables in the case of qualitative predictors. And so in this case, you will not need to do that. So that is nice. Um, Clearly, that is an advantage when it comes to understanding the model. Okay, so dummy variables can be somewhat complicated to understand and follow. Decision trees can also they can handle both numerical and categorical data. So that's an advantage as well. So whatever we can do with regression can be done with decision trees. And they tend to perform well even if um, some of the underlying assumptions are violated. And quite honestly, there are fewer assumptions than the assumptions we had for regression. So that's good. They tend to perform fairly well, um, and irrespective of the assumptions. And so that's a huge advantage because in regression you always have to keep that in mind. Now, there are some disadvantages for decision trees. So decision tree learners sometimes they can create complicated trees that may work very well for the data set that you're working with, but when you test the same model on, say, a new data that you have obtained, then it may not perform well on that. Okay, and when that happens, we say that we have a model that overfits. It overfits the training data, and then it does not perform well on the data that you get in the future or some other test data that you have set aside to test the model. So that is somewhat of a disadvantage. And so we always have to worry about overfitting the model. Um, and also decision trees, they may create bias trees if some classes dominate. So for example, if if you have a binary variable, for example, here risky and safe, and let's say for some reason your data set contains um, a higher proportion of risky class as opposed to safe class. Okay, so let's say your data set is 100 observations. Let's say 90 observations are related to risky loans, and only 10 are related to safe loans. So if you use that data to create a decision tree, clearly you have a huge proportion of um, one class over the other. So the decision tree will be biased for that class. Okay, so it will predict risky in a lot of instances. And so, for example, let's say it predicts 80 of 90 observations as risky and only misclassifies 10 of those observations. And so even if it misclassifies all 10 of the safe observations, then even so, you've predicted 80% of your training data correctly, right? But there's a problem because the risky class dominates in that data set. And that's not the only objective of the model. The objective is to predict both the risky and the safe class. So you want to be able to predict those 10 observations that are safe, right? So you want to be able to predict those correctly as well as risky correctly. So when you have class imbalance, then decision tree will be biased towards the dominant class, and that's not good. Okay, so you want to make sure that your training data has a decent distribution of classes, and not the case that one class dominates and then the other. Okay, so let's start the assignment prep and then we will go into how these trees are created. So for the assignment prep this week, step one uses credit card company dataset. This is the dataset that we used previously. And the variable, if you recall, we used was defaulting on credit. This was a binary categorical variable. So that's what we're going to use for the first decision tree model. And the model that we will create is often called a classification decision tree. So the reason it's called classification model is because we're going to try and classify observations either into the class default or not defaulting on credit. So that's why it's a classification decision tree. Later on, we will also do a regression decision tree in which we will be able to predict quantitative variables. So we'll start with step one, and in step one, when you run this, you will notice, first of all, it just loads the data set and prints the first 6 rows. So just like we've been doing before, but it also installs a package called rpard.plot. This package you can use to visualize the tree that is created. Okay, so if the tree is simple enough where it's not too long and not too complicated, then one can simply just visualize it by printing it. So this will be a very useful package later on. Step two is where we will split the data into training and testing set. So what is a training and testing set? Well, simply put, training set is the data that is used to train the decision tree model. And then once the model is trained, we use the testing set to test that data. And why do we do that? Why do we split your original data into training and testing? Well, because of the one of the disadvantages that I mentioned earlier, decision trees can overfit, and they can overfit the training set, the data set that is used to train those models. They can you can come up with a decision tree model that fits the training data very well, but then it fits it so well that unfortunately it does not perform well on any future data. So in other words, decision tree do not really generalize very well. And to go around this issue of overfitting, what we can do is we can use the training set to train the model, but then we can use a testing set, also called like a holdout sample, to get a feel for how is it doing on a data that it has not seen in its training. And together with the training and testing set, you can figure out um, an optimal kind of a solution where the model is not going to be overfitting. Okay, so that's why we do this step. Usually, um, what you do is you take your original data set and you split it randomly into, say, 70% or 30%, um, um, respectively, meaning 70% will be for training and 30% will be the testing data set. Here we're doing 60-40, meaning 60% of the sample will be randomly split um, into a training set, and then the 40% that's left over will be the testing set. Okay, so this step performs that. And so you can clearly see here, first we partition it, it's getting information on how many rows we have in the data set, and then what is the 60% of the number of rows. That would be the sample size. This would be the sample size for the training set, right? Because that is what the 60% is. So, and then you can use that and op, the function sample along with these inputs here to get a sample size of 60 of this. Okay, that's why we have size equals the sample size that got assigned um, the sample size, 60% of the original sample size. So that's your this sample would give you the indicators or the indexes that can then be used for on the data frame, the credit default data frame, to pick your training data. So this is your training data, and then we will print it. How many rows are there in the training data? And in a similar sort of way, once we now know where the indexes for training set, um, we can use that along with a minus sign. What that means is we're looking now inside this here. We're looking at indexes that are not training indicators. Okay, so this is everything that's left over, and that should be the 40% sample. So that gets assigned to the test data. Okay, so this is a way to subset the data. So here we subsetted 60% into training set, and then the leftover 40% into the testing set. And then we can use the nrow um, function to see how many rows are there. So when you print it, you'll see that we have on the training set 360 rows, and on the validation set or the testing set 240 rows. Okay, so 360 rows will be used to train the model, 240 rows will be used to test the model. Before we move to the next step in our assignment prep, let's talk a little bit about how is the decision tree able to do the split on a node to create the two branches. So clearly we know that somehow the decision tree takes the data as input and it's able to create these splits at several nodes. And we know that somehow it's able to do it optimally, but we don't know how. And I think it's a good idea to discuss that a little bit before we create the decision tree. So the way that works is that it calculates Gini impurity at each node. And one of the very specific measures of impurity is Gini index. The idea is very simple. It wants to split that data set into, say, two groups such that the impurity measure is minimized. Okay, so that, for example, if we're working with a variable that is binary, 0 or 1, then it would like to do a split in which it's able to take as many zeros and as many as possible and put it in one group, and then as many as ones and put it in the other group. Now, it will never happen at the first split because you will have data set that has variables, where we're trying to do that split will take different values for the binary variable 0 and 1. So for example, if we're looking at um, a loan amount and we want to see whether someone has or is current on their payments or is late on the payment, then that loan amount may have different values where people are current or late. Okay, it will never be the case that someone that has a loan of more than 10,000 is always late. Okay, so because of that, you can never get a perfectly pure data after the first split. So it always has to keep growing the tree, partitioning into more and more branches. But the way it's able to do that is it's able to calculate the Gini impurity measure, Gini index. And there are other metrics as well, but this is one of the very commonly used. So let's look into that a little bit. So for example, if we look at this example 8.2.3, so we see that we have here's the loan amount on the x-axis, and this is the previous historical experience of payments. Okay, whether the individual is current or paid off, or whether the individual is late on the payment or defaulted. So, and you can clearly see that for different loan amounts, um, we have some individuals that are current, some that are not. But how do we calculate, say, the impurity of this? And the way we do that is using this formula. So the formula is very simple. We take the proportion of the two classes, we calculate their percentage of the percentage of that class in the data set. We square them, we add them, and then we subtract them from 1. Okay, so for example, there are 19 observations here. So we have 1 minus the safe loans are 10 out of 19. So it says here 10 out of 19. So they must be the green ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the risky loans are 9 out of 19. So those are the two proportions. So we're going to square them. We're going to add them and then subtract that figure by 1. And so we get 0.499. That is the impurity measure for this data set. Now, keeping this in mind, if we scroll down, here's the algorithm, the way the tree works. So in the first step, and by the way, R part is recursive partitioning. This is the R part algorithm that R will use. So the first step is it picks one of the predictor features. Okay, so it will, it will pick any one, say, at random to start with. For that feature, it picks a value. Okay, so it'll pick any value. Um, so if the feature is quantitative, it may pick just like the example we did previously, where the loan amount was picked at 69,000, I believe it was. So it'll pick that value and then it will divide the training data into two partitions based on that. Okay. So it will say, for example, if the loan amount is less than 69,000 or loan amount is greater than 69,000, those will be your two groups. And then it will look at how many um, uh, of each classes are there, the safe and the risky. Okay, so we'll measure how pure each of the resulting portions are, where pure means segment that contains records of mostly one class. So it will basically calculate the impurity or the purity measure in that group. Then it will try different choices for the values of the predictor. So it will keep doing that. It will try different values to maximize purity. So it's trying to sort of minimize impurity by picking the threshold of the split. Okay, so it's just trying different thresholds. And then once it's able to do the minimization, it goes back, repeats step 1 through 4 on the remaining predictors. That is how it's able to pick um, sort of like an optimal split. So now that this is probably a little bit clear, we will now run this algorithm so that it will make sense now how it's doing those splits. And again, we use different metrics for measuring that purity. And clearly, in the case of regression, it's going to be slightly different, but the idea is the same. It's just trying to pick the value of the predictor that gives um, the most optimal split that's possible. So let's go to the next step in assignment prep and run the tree and see what we get. So we will now create the classification decision tree in step 3. And in this step, we will use the rpart library and a function in this library rpart to actually create the tree. So that function is given here. So it takes several of these inputs, and this should be very familiar. This is the model that we're trying to create. We're trying to create a model for default using missed payment, education, and age as predictors. This is a classification problem because we're trying to classify observations into the two groups for default, whether an individual defaulted or not. So that's why we're going to set method equal to class. It's a classification decision tree. And another parameter we're going to set is the min split. We're going to set it to 10. And by the way, this is incorrect here. It should be 10, shouldn't be 15. Um, so what that means is the minimum split is the minimum number of observations that must exist in a node in order for a split to be attempted. So basically, when the tree starts creating the nodes and the branches and keeps splitting the data, um, if it comes across a node in which we only have or we have fewer than 10 observations, then it's not going to try to split that node anymore. So there are many reasons we want to do that. For one, we don't want very we don't want nodes that have very few observations. And second, this helps the issue of overfitting as well. So we will get a model that uh, you know, well, it still can overfit the training set, but this certainly helps, okay, setting a minimum number of splits. So this is being set here. And then once the model is set up, we will use the print CP option to get the output of that model. So let's go over this output now. So here's the output that we get. And in this output, the most important part is this table that's given here. And in this table, we will focus on two columns, CP and X-error. X-error is essentially the cross-validation error. And as you know, we're using the training set. So far, we haven't used a testing data set at all. We're just using the training set to train the model. Cross-validation is a method in which the training set is further split into a train and test. And in this case, I would not call this a testing set, but I would call this the split to be train and holdout or validation. So the training set itself is further split into a training set and then a validation set. The training set is used to train the model. Then then the model is used on the validation set to do the predictions, and then the errors are calculated, how many observations are being predicted correctly, and so forth. Now, our part uses a special case of cross-validation called um, tenfold cross-validation. And what that means is tenfold is essentially an example of the general case of n-fold, that is an n-fold cross-validation. And um, in this way of cross-validation, the steps are fairly the same. The first step is always to take your data, like for example here, you take the training data and you shuffle it randomly. You then create, you split that data set into n groups. Okay, so in this case, we would split it into 10 different groups. And then for each group, for each of those 10 groups, we take that we take that one, the first group, let's say, as a holdout or a validation set data, and then the remaining 9 groups would be the training data. We would fit we would then fit a model on those training sets and then evaluate it on that validation set. Okay, and then so that evaluation can basically be how many of the observations are predicted correctly. Okay, we would retain we would then retain that score and discard the model, and we would basically repeat that process for all groups, um, taking them uh, as a validation set or a holdout set. Okay, so you take one group, use the other groups to train a model, test it on that validation set, and then repeat this process for the remaining groups. All right, so fairly simple. This is what cross-validation is. And in the case of cross-validation error, you're trying to see because we're calculating the error, so we're trying to see how many observations are misclassified. Okay, and at the end of this, we will summarize the skill of the model basically by just summing those errors. Okay, so that would give us a cross-validation error. So that's what this column represents. Now the CP here, CP is essentially a complexity parameter. Okay, so and it's essentially used as a stopping criteria. So you want to stop at at some point you don't want to you don't want the tree to just keep growing. You want to stop at some point that um, makes sense for the general case. Okay, and cost complexity parameter will help you do that. So essentially here, um, what we want to do is we want the CP value uh, that is associated with the smallest tree. Okay, so we don't want the tree to keep growing. Okay, so we want the CP value that is associated with the smallest tree and has the smallest cross validation error. That's what we're looking for. And the tree size, you can see here, and split, the size is given here. So we want to be able to pick a CP value that is associated with the smallest tree that has the smallest error. That's the idea. All right. And so really what this is it's a trade-off between the size of the tree and the error rate to basically prevent overfitting because overfitting is an issue with decision trees. Um, Large trees with low error rate are kind of penalized in favor of smaller trees. Okay, that's what we're looking for. So that's what these columns represent. So we're not going to be, well, we can make a decision right now looking at this table, but this decision is much more simple if we get a visual, which is what the next step does. So in the next step, we will take the cross-validation error and the cost complexity, these two columns, and we will get a plot for them so that we can see, um, you know, um, we can see how the decision is going to be made for picking the CP value. So here, so we can see here, this plots the cross-validation error against cost complexity. So the cross-validation error is on the y-axis, cost complexity is on the x-axis. So this will give you or assist you in selecting an appropriate model by pruning the tree. Pruning essentially is the idea of um, uh, giving preference to smaller trees over the larger trees that may overfit the data. Okay. But obviously, we don't want to pick too small of a tree where our cross-validation error is large. So we have to be careful with this. A horizontal red line is drawn on this that is one standard error above the minimum cross-validation error. Okay, so it's one standard error above the minimum error that we have on the cross-validation. So this is the red dotted line. And I can kind of see that this is the minimum error that we have. So it's one standard error above this. In general, the largest CP value that achieves a cross-validation error below the red line is chosen to prune the tree. Okay, so below the red line we have three of these, and we want to be able to pick the largest CP value that has an error below this red line, and so clearly is 0.039. And if you look above here, um, point, 0.039 CP is going to fall somewhere, I would say somewhere between 2 and 3 here. 0.039 would be between this and this, right? So um, uh, we're expecting the cross-validation error to be the minimum here or below the red line. Well, it is the minimum error is 0.035 or 0.35, and that error is given here. So we can see that we're falling here somewhere, right? So that's how you pick your CP value. And then once you pick your CP value, we're going to prune the tree. We're going to pick the tree that is associated with the CP 0.039. So you prune the tree by, again, recreating the model, but this time giving an input of CP equals 0.039. Okay, so this is an input to the model this time, and you rerun it, and you see here CP of 0.039 is associated with a cross-validation error that's 0.3396. So this is the tree that we're going to pick. So you can see this is a smaller tree than this tree that we had. Okay, but the error here you can see was increasing. So there's really no point to do that. We can just stop here, and that would be an optimal tree for us. So now that we have pruned the model using the plot of cross-validation error against CP, we were able to pick the CP value that's most appropriate, put it in the model again, get the prune model here, and get the table again, and we can see that this is a smaller tree but has a lower cross-validation error compared to the previous tree that we created. So we can now visualize this tree. So we can get a visual of what the tree looks like. Now, when you're working with real world data sets where the tree has to be large, this may not be possible to do, but at least you can see, you can visualize the tree that we just created and know that, how the R part function works. So in this step, each node will show, so first we'll get a visual, and here's what the tree looks like. And in each node, we have the predicted class, whether it's default or no default. So this here, for example, says yes, yes, that's all. Uh, Basically, the majority of the observations there are default, and majority of the observations here are not default. We get the predicted probability of the event defaulting. That's for example, here is overall is 0.56. Then we have 0.74 and then 0.92. So you can see that as the split happens, the probability of each class here, uh, well, probability of defaulting increase. Okay, so that's what we want. We want the tree to be able to split this data, remember, based on that parity method. And it is able to do that because most observations here are default, and the probability of defaulting is 0.92 in this terminal node. Compare this to this here. Most observations are not default and or not defaulted, and the probability of defaulting is low, right? And that's what we want. We want classes to be as separable as possible, and that is what the tree is doing. So actually, it's actually doing what we think it should do. So this here is how we plot the tree. So we're going to use rpart.plot library, and then the method is also rpart.plot. We're going to plot the prune tree, not the original tree that we created, and this is what that looks like. Okay, and then here I've given some interpretation of the tree. So please make sure to go over this. This is what I just explained just now. But mainly, once we have the tree and we know it's the pruned tree, so it's the most optimal tree for the data set, um, the next step is to evaluate the model. And how do we evaluate a classification decision tree? Remember, we're basically predicting a binary uh, variable, a binary categorical variable. Well, we can use the confusion matrix just like we did last week. We have binary predictions, 0 or 1, and so we can use the confusion matrix that we used in logistic regression. So again, this is all information that you know, and we're going to use the pruned model, okay, not the original model, the pruned model, on the testing data now. Okay, so we're going to predict the testing data. This is from step 2, I think it is. Yep, in step 2, remember we split the data 60-40%. The 40% was the testing set split, and that's what we're going to use to do our predictions and get the confusion matrix, because we want to see how the model performs on the data it has not seen before. Okay, so that's why we're using that. And then the prediction type is class. It's a classification prediction. This step here, all of these lines, they construct the confusion matrix. and then we print the nicely formatted matrix that's given here. So our model, as you can see, the rows here represent the actual um, data points of defaulting, yes or no, and then the predictions are in the column. And so the first cell here is the actual data points were no, and the prediction was also no. There are 93 of them. That's good. That's a pretty good proportion to fall in that cell. And then look at this cell diagonal to the first one. This is where the actual defaults were yes, and the prediction is also yes. There are 96 of those observations. So that's good. Most of the data points are being predicted correctly. And then there are some um, predictions that are incorrect. So you can see here the actual data points were where the default was yes, but the prediction came out as no, and then vice versa here in this one. But most of the observations are being predicted correctly, so that's a good model that we just created. And then you can use these values here in the confusion matrix to calculate the accuracy, the precision, and the recall. Okay, and that would be your task um, to do. And then now that we know we have used the training set to train the model, then we pruned the model, then we tested it on the testing set, and we're happy with what we see here in the confusion matrix. So now we can use this to predict, um, future cases, or like in this case, we're creating data frames of one row, where, for example, in this case, the missed payment is set to no, education is postgraduate, and age is 42. So we predict that one row here using the prune model. And then here's another prediction. And so the prediction then would come out as either one or either no or yes. So you can see here in the first case, the prediction is no. In the second, the prediction is yes. So this is the classification decision tree. Again, we start with splitting the data into training testing set. We use the training set to train the model. We look at the output, specifically the CP value and the cross-validation error. We get a plot of cross-validation error against the CP value. We pick the most appropriate CP value at which the cross-validation error is minimized or is below that red line. We pick the largest CP value where the cross-validation error is below that red line. Then we use that CP value to create the model again, and that CP value goes as input into the model creation. That is going to be our pruned model. It's the pruned decision tree. We use that pruned tree to get our confusion matrix on the testing set now. This is the 40% split that we did earlier. So we get our confusion matrix, we calculate the metrics, all of those stats, we to see how good of a job the model is doing in prediction. And if we're happy with it, then we can do our predictions using future data or data that is going to be asked in the questions. So that's how classification decisions tree work. And in the next step, we will now get into regression decision trees. So next we move on to the regression decision tree that will be used to predict a quantitative variable. And so we're going to work with a different data set now. And this is also a data set that you've used before in one of the earlier modules. This is where we will be predicting the wage growth based on these other variables like inflation, unemployment, economy, and GDP. Now remember, when you do these predictions on this data set, these numbers are in terms of percentage. So for example, when you print the data set, 7.30 here for wage growth means it's 7.30%. Okay, so that's how the data was given to us. Okay, so after you've run step 8, we can go to step 9, where just like before, we will do a split into the training and the testing set. So the original data set will be split. 80% of it will be the training set and 20% will be the testing set. And again, we're doing this to and to be able to test our model on the testing set to make sure that it doesn't overfit the training set. Okay, so once you run this step, you will see that in the training set you only have 79 rows, and the testing set you have 20 rows. Okay, so it's a small data set, but this is good enough to do this analysis. So in the next step, step 10, we will construct the regression decision tree. And in this step, the you will notice that the modeling part is pretty much the same. We're using our part. The model input is the same way as before. We're trying to predict wage growth using economy, inflation, and GDP. The R part control, the minimum split is again set to 10. And this time we're using train data 2. That is what was used here to input the training set for this other data set, because as you know, we have two different data sets in this problem set. Okay. The only difference here is that the method now is not class, it is ANOVA, and this will allow us to do the regression decision tree. So after you run this step, you will get an output. So let's go over what that output looks like. Now, before we go to the output, I do want to mention that previously in the classification decision tree, the splitting criteria was Gini index, which is a measure of impurity, right? So if you recall, we were comparing the impurity of a child node compared to the parent node. That's how the algorithm was doing the splits. For regression decision tree, it's slightly different, and the idea is to calculate for a given node to calculate the sum of squared totals. Okay, so SST. And basically, it's very simple. For any given node, you take all the observations that you have in that node. You look at the response variable. So in this case, it would be wage growth. You calculate the mean of the wage growth for that node. And then you take each observation, you subtract that mean, and you square the answer. Okay. So basically, when you take each observation, you subtract the mean, you're kind of getting a measure of how far the observation is from the average. And then you're just squaring it. So if you get a negative answer, you square it. You get a positive answer, you square it. And then you sum across all of those observations in that node. So that is the sum of squared totals. Okay. And the splitting criteria is you take the sum of squared totals for the parent node and you subtract the of sum of squared totals for the left node and the right node. So you take the left node and the right node, you add them together, and then you subtract that answer from the sum of squared totals of the parent node. That is the splitting criteria, and uh, the idea really is that you're trying to choose the split to maximize the between groups sum of squared, which is the case of analysis of variance. Okay, so that is what is used for splitting in regression decision tree. So now that we know this, let's go to the output and see what kind of table we get. So here is the output that we get, and you will notice that the table looks very similar to the one before that we got in the classification decision tree output. So you have the cost complexity parameter column here, and this is the cross-validation error. And you can clearly see that at some point here, that error is minimized, and we would like to make sure that we pick a tree that is not too complex. So it should not be too complex, and the error should also be minimized. So In order to do that, we will first plot the cross-validation error against the cause complexity. So just like before, we're going to get the same plot for this model. And when we do that, we get the plot that we are now familiar with, and we plot this line. And as we suggested before, that the best CP value is the largest value at which the error is below that line. And so clearly that happens to be at 0.019. So, and you can see after this value of CP, the error decreases slightly, but there's not really much of a gain. So we're going to stop here so that the tree doesn't get too complicated and doesn't overfit the data set, which is the reason why we stop at the largest value that gives the the minimum error or the one error that is below this line. So um, that is the criteria. The first time the error goes below the line is at this value. And so this is 0.019 is the one we will pick. And then again, just like before, we will reconstruct the model. And this time we will input CP to have that value of 0.019. And then this is the pruning of the model, right? So we get the prune model, and the model looks like that. And the error again now is minimized here at 0.218 for that CP value. So that's the model that we're going to use. So next, just like before, we will use rpart.plot to plot this model. And so here it is, and you can see now we're splitting um, on GDP. Here on the right side, we split on GDP and then inflation, and we get these terminal nodes. And just like before, the percentage is simply how many observations are in this node. What percentage of observations in the node are relative to the original sample size. And this is the predicted value. Okay, so if suppose our GDP is not less than 4.5, so we would go here. And then again, let's say with GDP this time is not less than 8.8, so we would go here. And if inflation is not 7.3, so then we would go here, and the predicted value in that case uh, for for this scenario that I just went through, the wage growth would be 9.7%. Okay, and you'll notice that this plot, by the way, only prints yes and no's once here. So the left side is always yes, the right is always no. So for example, in this split, this side is yes, this side is no. Okay, so that's the predicted value, and just like that, we have these predicted values for different terminal nodes. And you can see that the predicted value of wage growth sort of increases this way, right? Well, that's what the tree is trying to do. It's trying to differentiate between large wage growth and small wage growth. And it's trying to decide what variables and what thresholds of those variables determine those values. So clearly, it's much more intuitive and um, much easier to understand. So next, we're going to create root mean squared error, and it's a very simple calculation, and this is one way to evaluate the performance of your model. So what you do is you take your model and you do your predictions. So for each observation, you do your prediction. And then for individual observations, you take the predicted value, subtract the actual value. So in the case of wage growth, you'll take the predicted wage growth. Um, you subtract the actual wage growth, square that answer. And so if you recall, this is simply just a residual. So you do this for uh, each row in your data set. You get the prediction, subtract the actual value, square the answer, sum them all up. So sum the squared of residuals divided by n, take the square root. That's the RMSE, root mean square error. Now, the way we're going to calculate this is using an R function that you will create yourself. So these are user-defined functions. And R, this is one of the very powerful features of R. It lets you create functions on your own. Just like our part was created by someone for us to use, you can create functions that you can use or others can use. So here we're going to create an RMSE function. We're going to first um, say what the name of that function is. So it's RMSE equals function. So this tells R that this is going to be a function. And then we have two inputs, the predictions and the observations. These two inputs will be given to this function, and the function will return this. And this is essentially just the RMSE here. Let's see. So we have the predict, we take the prediction, we take each prediction, subtract the actual value, square it, sum it. Okay, so this is the sum. Then we divide it by n. Okay, so the either length of the predictions or length of observations, they should be the same. And then we square root, take the square root of that entire sum divided by n. Okay, and that's your RMSE, and you return it. So essentially the function takes predictions and observations as input and returns the root mean squared error based on this formula. Pretty neat, right? So you can create this function on your own, and then we use the predict function in R. We give it the pruned model that we just created in the previous step. We give it the test data. We're going to do the predictions on test data using that model. And we want the output to be a type it's a vector. So make sure you read up on what an R vector is. And it's basically just a list of the predictions. Okay. And then you save the predictions here. And then you use your function RMSE that you just created here. The first input are those predictions that you just did. And the second input is the actual observation. And they can be referenced using the test data and then the dollar sign and wage growth. So these are the actuals. And you save the answer in RMSE variable, and then you can print it. You round it to 4 decimal places and you print it, and you get 1.0558. You want this root mean squared error. Clearly, if our model is doing a good job, the predictions will be close to the observations, the actual observations. So this will be a very small answer. Square will be small as well, and when we divide it by n, that will be small, and then the square root of course will be small. So we want smaller values of root mean squared error. In fact, if you had the perfect model where the predictions were exactly the same as observations, your root mean squared error would just be 0. And then you can do your predictions. So again, we create the data frame. So the first case is when the economy is not in recession. Inflation is 2.1, GDP is 2.5. We use the prune model 2, which is the regression model, um, using that new data here. Type is vector again. We get our answer and round it. So we get 4.2027. So that means the wage growth is 4.2027%. And then when the inflation is slightly higher and the GDP is much higher, again, there's no recession. The wage growth increases to 7.0595.